All right, so it's time. Yeah, it's my pleasure to introduce Professor Antonio Celani, who will be telling us about reinforcement learning for airborne wind energy. So Professor Celani, you may start when you're ready.
Thank you, Siddharth. So thank you for having me here, even if virtually. I must say that I really miss being at ICTS. I have been a regular visitor over the past 10 years or so, and I hope I'll be able to meet you all again at ICTS soon. Okay, so my talk today is about a line of research that started a few years ago, and from a very basic idea. This basic idea is that the atmosphere is an out of equilibrium energy reservoir. So there are means to extract energy from this reservoir, and so some applications you might be very well familiar with, such as what you can do when you exploit thermal updrafts for your paragliding experience. This can be turned into technological applications. So an initial part of this work was to understand how to exploit turbulent currents, which offer great opportunities because there's a lot of energy contained in the atmosphere, but also great challenges because this energy is often unpredictable, and things can turn out to be very bad if you don't do the right things at the right time. So lately, in a spin-off from this original project, with my group of students at ICTP, who are listed here, and especially thanks to the exceptional work of Nicole, a master student of mine, who basically single-handedly took this project in her hands when it was just an idea. We were considering how to apply the same idea, the same approaches to airborne wind energy extraction. So since you might not be familiar with this idea of airborne wind energy, I will spend some time in trying to introduce you to the subject and give you a motivation for our work. So what is airborne wind energy? So we are quite familiar with this way of extracting energy from the atmosphere, wind turbines, which are often arranged in wind fields or wind farms. These are quite reliable ways of extracting energy. They have some serious shortcomings, though. The first thing is that structural properties. So they are at most large, high as much as 200 meters. That's basically the maximum height that can be obtained roughly without incurring into structural instabilities. These structures are typically very heavy. They are clearly very static. Okay, so once you choose a certain location for your wind farm, that's it. Okay, and then there are also additional issues that one might consider as relevant or irrelevant. Most people consider them to be very relevant, like the impact on the landscape or the noise that they can make. So airborne wind energy tries to take a very different approach to the mechanism of energy extraction, which by itself is lightweight and portable. So what is the main tenet of airborne wind energy production? So the idea is to use flying devices, flying airfoils like kites or even sailplanes or gliders that are tethered to some object on the ground, which could be either, as is shown in the left, a station which produces energy and stores it. We will see in the following how these things actually work in practice. Or it can be directly used to help towing vehicles, either on the ground, but most often on the sea. Okay, so the area which eventually we will be focusing on this talk is this one in the right panel. Can we use structures as kites in order to have an auxiliary source of propulsion for sails? So the key points of airborne wind energy is that these are lightweight objects, so they are easy to transport from one place to another. They are infinitely less expensive as devices than wind turbines. And one conceptual aspect that is also very important is that typically wind turbines do not have much opportunity, do not give much opportunity for control, so for fine-tuning their behavior depending on the current state of the atmosphere. Whereas airborne wind energy typically can and has to be dynamically controlled in order to extract energy from the atmosphere. What is dynamical control of a kite? Well, you just have to pull the lines, to pull the threads that connect your station or your ship to the kite in order to maneuver and to move it in such a way to extract as the maximum possible energy. And last but not least, it's been proven at the level of prototypes that kites can be driven as high as several hundred meters. And in the atmosphere, at least in the atmospheric boundary layer, the higher you go, the stronger the winds are. And so the more energy you can actually capture by this means. So typical ranges, desired ranges of activity for these kites would be in the 700 meters or so. So below the inversion, but still well within the turbulent boundary layer. Okay, so let's go and look in a little bit into detail into these two examples, and then we will spend an extensive time on the towing model of an airborne and wind energy. I have to mention also that there's in the last 15 years, there's been a lot of companies trying to build actually commercially available solutions for both in these two settings. So you can see all sorts of varieties and geometries for these objects, including kites or delta wings or planes, multiple kites, etc. So it's a really flourishing field from the viewpoint of engineering solutions. But of course, here we will take the approach that we are able to take, that is to think about the conceptual aspects of this problem and how we can introduce new ideas to the field. Okay, so hopefully, if I'm able to go to the next slide. Okay, so this is an example of what an actual ground generator works. So you can see that on the left picture. So there's a kite which is attached to an actuation unit. So the very fundamental idea is that if the kite is in a situation where it's passive, so basically the lines are left to extend, and as they extend, they make turn these cylinders which are available here, and therefore you can turn this kinetic energy directly into electrical energy. Of course, this cannot go on forever. So at some point you will have to re-lean the kite, and this typically will cost you energy. But the idea is that if you do properly at the right time and place and with the proper choice of maneuvers, you can have a overall a cycle that delivers energy. So the energy that you get while in the reel out phase exceeds the energy that you have to provide in the reel in case. But like I said earlier, today we're going to fix our attention on to the problem of auxiliary propulsion, and I will briefly comment on the problem of ground stations at the very end. Auxiliary propulsion is a reality. So this is a snippet from an advertisement, basically from this company, Sky Sails. They conducted extensive trial sessions in the ocean close to Australia. And what they found is that basically these systems could reduce energy consumption by a quite impressive 20%. Just to put this thing in perspective, all the kind of things that you can do trying to optimize over the hydrodynamics of the ship under the surface typically deliver you a few percent increase in drag. So we're talking really about different figures. Okay, so this is essentially our motivation. So when we abstract away from this problem, basically our main objective is to maximize the distance traveled or the average speed traveled in a given direction over a certain time horizon. Okay, so say you're interested in the next hour to obtain the longest possible distance along the wind direction. And you want to achieve this by choosing how to maneuver the kite, so how to change the pose of the kite, to change the relative position of the kite with respect to the ship by using the lines. And you can clearly see that this problem is essentially cast as a problem of optimal control. There is a dynamical system which in this case is extremely complicated, extremely complex, because it couples the atmosphere in general with the dynamics, the aerodynamics of the kite, the mechanics of the lines, the tethers that connect the kite to the ship, and then the hydrodynamics of the ship itself on the sea. So this is extremely complex to address in itself. But nevertheless, if you think of it as a dynamical system, what you want to find what are the optimal controls. And the controls are exactly the way that you maneuver your lines, the way that you pull your strings in one direction or another in order to change the relative position of the kite with respect to the wind. And of course, on top of all this, you want to deal essentially always with turbulent-like conditions, because if there are strong winds, that's going to be turbulence. Okay, so this is inherent to the problem. Okay, so when you see it as a problem of optimal control, then you basically go back to the textbooks and look at what can be done in order to optimize your behavior, the behavior of your dynamical system with this class of definite goals. And then the idea is to use techniques from classical optimal control. So in short, the idea is that you have some dynamical system where these Q variables represents all the degrees of freedom of your system, which again, it's a humongously large number in the system at n, because it includes all the degrees of freedom of the turbulence and the mechanical degrees of freedom of the kite, the line, the ship, etc. But nevertheless, you assume that you can write such equations in form of a very complex partial differential equations coupled to continuum mechanics. And then in an abstract sense, your goal is to find, so here you see that this F describes basically in an abstract form what all the dynamics of the system is. And it depends on the degrees of freedom themselves, this Q, and on other variables, which are the controls. Okay, so these controls, you can think of them as the forces that you want to apply to the lines in order to drive the kite in one direction or another. And then your objective in general is to maximize an integral over time. So from the initial time to some final time, some time horizon over which you want to optimize your task, which could be, depending on the task, on the order of minutes or hours or days. It depends. Of what? Of some function, which we're going to call a reward. So it's you can think of this as the opposite of a cost. Okay, it's a reward which may depend on explicitly on time and of course on the current configuration of your system, Q of t, and on the current controls. Now, this optimization has to be done over all possible functional dependencies of these controls over this time horizon. So as it is, it seems quite a daunting task to find this optimization, to solve this optimization problem. But in fact, it turns out that there are ways of casting this optimization problem in terms of solving a set of equations. So depending on whether the system is deterministic or stochastic, there are different classes of problems. There's a huge literature. So this is, in a sense, in an abstract sense, this is problem solved. So as long as you're able to solve a set of optimality equations, which go under the name of Hamilton-Jacobi-Bellman equations in general, as long as you're able to solve them, you will be able to find the optimal control. Okay. So problem solved? Well, not really, because as you can imagine, so there's a first hurdle in that if the system is high dimensional, the solution of this Hamilton-Jacobi-Bellman equation is basically unfeasible. Okay, so that's one first hurdle. It's what is usually called in the control community as the curse of dimensionality, in the sense that the complexity of a solution of this set of equations, which is typically done through a technique which is called dynamic programming, explodes in your hands as soon as the degrees of freedom become very the number of degrees of freedom becomes very large. So this is one practical issue, if you wish, but there are other more conceptual and I think more prominent difficulties and limits in this approach to classical optimal control, which you will find somehow also the same class of approaches can be called also predictive control theory. It's essentially the same class of approaches. So the first, So there's a series of problems in trying to implement this approach. So in order to solve for the optimal control, you must know a priori what the dynamics of your system is. And this means that you must, at some point, adopt a model. Okay. Since, sorry, just a second. Since you need to solve basically the dynamics of your system in order to predict what will be the future configurations, you need to know what the dynamics is. And typically and it's quite evident in the system at end, the kind of description that you can give of such a complex system when there is a lot of complicated fluid structure interactions is essentially a very difficult task. So you can adopt some model, but you cannot ever be sure how good the description is about how the drag of the ship in presence of waves is correctly defined, or how to describe exactly the mechanics of the kite without making often very crude approximations. Also, the dependence of the rewards in general on the variables at end, on the controls, and the degrees of freedom might be quite complex in its analytical form. So this is an even more dramatic problem, because it does not even allow you to cast the problem properly in terms of classical optimal control theory. And then an additional source of difficulty is that, like I said before, you would need to have access to the full configuration of the system. And this is often an enormously high dimensional space. So not surprisingly, starting from, so basically the theory of optimal control in more general form was developed by Richard Bellman in the 1950s. And since then, it clearly emerged from the beginning that some other different kind of approach was needed in order to tackle real life problems in which you want to identify an optimal control. And then I would say that starting in the late 60s, beginning of the 70s, and culminating in the 80s and 90s, then a theoretical framework has emerged that actually answers to the following two questions. Can one find the optimal control without knowing exactly from a priori what the dynamics of the system is and what the expression of the rewards are? Can you find effective controls even if you do not have access to the full state space, as it's called in the jargon, so to full access to the observables in your system? And this framework goes under the name of reinforcement learning. And the basic idea of reinforcement learning in this model-free formulation is that this model knowledge, which you would have to know a priori, you can replace it with empirical data. That is, rather than trying to predict what happens, you will interact with the environment and sample the environment, right? So the idea is that it's very similar to the kind of idea that you have when you do a Monte Carlo simulation. You rely on trajectories that are produced by interaction with your very complicated system, and then you try to perform some data analysis, some procedure on this data that you obtain that will allow you to discover what are the best controls that you can possibly do. So this is usually summarized in this graphical scheme in which there is an agent, which for us could be, for instance, the kite. And this agent makes some actions. Actually, there are some controls which are operated on the kite. And these controls generates consequences. And these consequences are changes in the state of the agent with respect to the environment. So if you try to pull one line, the kite will move on its side, for instance, and this will change the relative position of the kite with respect to the wind. And it will induce a different force, tension force in the cable, in the tether that connects the kite to the ship. And this will in turn, in its turn, change the kind of observations that the agent can make. So all the sensors that you can place on the kite, on the ship, etc., we make different recordings as a consequence of the actions. So there is a closed loop feedback of the agent through its actions and responses by the environment in the form of observables, which combine rewards and contextual observations. And the basic idea is that there are algorithms that simply by interacting with the environment, so without any knowledge of what the actual dynamics is, so the environment, you can think it as acting as a black box. The agent just receives some observations, some percepts, and then decides to make actions depending on those percepts, but there's no point whatsoever in which you need to open the box of the environment and therefore look into what the model dynamics is. Of course, should you have a very accurate model of the environment, this would lead to a faster learning process. You would be able to learn or to predict optimal controls in a much more efficient way. But in typical situations where there are many degrees of freedom, which range, of course, from engineering applications like this one to more computer science-based applications like playing table games or playing video games, the complexity of the environment puts the system very, very far from the reach of being able to construct a viable model of what is really happening. Okay, so this is the first qualitative answer to the problem. So what is not known will be replaced by empirical knowledge. And the second thing is that how can we deal with partial observability? With the fact that we do not observe in full the degrees of freedom of the system. Well, there are two main approaches to deal with this. They all go under the technical name of function approximation. Which, as you can easily imagine, is the idea that if I get a very high dimensional input, I must somehow find a lower dimensional representation of this input in order to be able to search for good ways of controlling the system. Now, if you're a physicist, the closest analogy, I think, is what you do with a gas, right? A gas is specified by a large number of, huge number of degrees of freedom. In the simplest case, just positions and velocities of each molecule in the gas. But you know that if you want to build a machine which extracts energies just like a Stirling engine or whatever, you know that you can rely on a few observables. You just need to know what's the pressure, what's the temperature, what's the volume. So a few degrees of freedom actually subsume all the knowledge of this high dimensional space of variables. So the idea of functional approximation is exactly that. So it starts with the assumption that this complex system actually can be described in terms of a relatively smaller set of relevant observables. And when trying to do this approach of trying to reduce the dimensionality of your system, you actually can take two different routes. There are also sort of ways of doing something in between, but for the sake of clarity, let's consider them as very separate in spirit. So one approach is just to select some observables. Okay, so out of this enormously large space of degrees of freedom, you just select some observables which you think are relevant. Okay, you have good reasons to believe that they are relevant. We will see later on the example of our situation, but just to anticipate a little bit, for instance, you think that the posture of the kite with respect to the ship or with respect to the ground is going to be a relevant information, right? So if the kite is very tilted on the right, then the kind of things that you can and will do are strikingly different from the ones if the kite is in a more neutral position. So this kind of intuition. So you also think that the relative velocity between the kite and the wind is also going to play a role in determining how your kite is staying up in the air and how it's able to pull to tow your vehicle. So you can reason in these terms and try essentially by a procedure guided by intuition and sometimes trial and error. So you try some observables, you see whether they work or not. And then you reduce basically by hand the dimensionality of the system. So what are the plus and minus of this approach? So the plus is that if you do such a decomposition, which I will explain in a second why it's called linear, but it's feature based in the sense that you identify your favorite features of your high dimensional space. The reinforcement learning approach has very solid theoretical guarantees, which I can summarize in a very sloppy, but I think maybe in insightful statement, is that the problem is, the optimization problem is convex in this case, okay? without any pretense of making it as a very mathematical clear statement, but that's essentially the idea. One big advantage of this approach is that what you find is clearly explainable. It's explainable in the sense that you selected the observables, and these observables are mapped into decisions, into controls. Therefore, this clear connection makes the system very transparent. And then, last but not least, these systems, by their inherent nature of being relatively low dimensional, are much easier to train. So you need much less interactions with the environment with respect to a system or a model which has a huge larger number of parameters for the control. What are the minus? Well, one minus is that, of course, you can get good results as long as you are able to identify the proper observables. Okay, so that's what it means, that it depends crucially on domain knowledge. And this dependence on domain knowledge actually in general in generally does, limits the kind of performance that you can achieve. Okay, so that's the first thing. Just excuse me a second. Sorry. So what is the complementary approach? The complementary approach to this is to rely on a different set of approximators. So rather than selecting your features, you use what are called nonlinear universal approximators. And the better known example of this is an artificial neural network. Okay. So this is the combination of these neural networks with reinforcement learning is the one that has actually achieved impressive performances in very complex settings like video games or board games. What's the big advantage? Well, is that you do not really now need to input domain knowledge, because the kind of observables that are relevant will be actually discovered by the training of the neural network itself. Okay, so the encoding of the feature is done as part of the training itself. So you can really start from scratch, right, with zero knowledge of your system, and then just by pure repeated interaction with the system, you will be able to learn what to see basically and how to act. There are impressive performances which are observed. They're at the expense of fewer theoretical guarantees. So typically these problems are a priori non-convex. They may turn out to be empirically convex for some reason that we still don't fully understand. But definitely these are black box explanations. So you can predict, you can find out very good performances, but the process of understanding why so, what the system is actually doing, is very painful in itself. Sometimes you can open the box and get a meaning of what the system is doing, but in most cases, this is a daunting task in itself. Of course, these kind of approaches are extremely data thirsty, so you have to supply an enormous amount of information in terms of data in order to train your system, and of course, a lot of computational power, because that's what it needs. So before moving on, I want just to focus on one specific point, is that I put the fact that dependence on the domain knowledge as a minus, because it's customary to do so, but I would like to think about this a little bit deeper with you. So is domain knowledge a bug or a feature? So from the viewpoint of computer scientists, the fact of relying on domain knowledge is usually seen as a pitfall or a dreaded necessity. This is mostly in the eye of a modern data scientist or modern computer scientist. In the past, in the 80s, there was a strong push towards domain knowledge with the creation of this knowledge databases, which, however, had a very, very difficult evolution, and therefore were really set aside in favor of a more ab initio approach to the interaction with data. But I would like to argue that for physicists and for engineers, the fact of relying on domain knowledge is actually a big opportunity, because that's where we can weigh in with the intuition about what the physical system is doing and what could be the relevant observables, and most importantly, by using a system that can be explained away. Okay, so all of this was very was extremely general, if you wish. So you might wonder, but how do these algorithms actually work? So what do they do in practice? So I would like to spend a couple of minutes by giving you an example of the algorithm that we actually used in the results that I will show in a second, which give you a sense that the idea is actually extremely simple. The idea that's behind the reinforcement learning. So this is a typical algorithm. There are many different variants, including also the most famous, probably Q-learning. This one is called SARSA, which stands for, it's an acronym for state action or reward state action. So the key ingredient in these and other algorithms is that you have to start with an estimate of what will be the total amount of reward that you can collect over this period of time during the evolution of the system. So the idea is that if you start with a certain configuration and make a certain decision at a certain time, what will you get from that time onwards? And this is, of course, you don't know that a priori, because if you knew that, then you could predict and you could optimize. The point is that you don't know that, so you have to start with a guess. And this guess initially might be very, very trivial. Like, I don't know, you don't expect to get anything out of the system. So all these Q values are 0 everywhere. So once you start with this initialization of your function, this quality function or state action value function, Q, you start interacting with the environment. And so typically the interaction with the environment is divided into episodes, and episodes is just a stretch of time from your initial time 0 to your final time t. Okay, so that's a sequential interaction with the environment. At the end of the episode, you start over again with a new episode, but you keep memory of what is going on. Okay, so you learn by keeping memory of what has been going on in a very specific sense that I will make clear in a second. So within a certain episode, you make a loop over time. So from the initial time, you go onwards. And at each step, interact with the environment. Okay, so that is, you make an observation. So you receive from the environment some contextual information through your observables. In our case, through the observables that we have decided. So let's measure what's the configuration of the kite. Let's measure what's the direction of the wind with respect to the kite. So let's use all this information to define our current context. Then we use this estimate of the long-term return to produce an action. So typically, for instance, you can use a Boltzmann distribution using these Q functions as energies and using some sort of numerical temperature, effective temperature for your system. Clearly, the idea is that when you get increasingly better estimates of the actual return that you will get from your system, you can slowly anneal your temperature to 0. So you will be picking up only the best action exactly. But at the beginning, since you're very uncertain about what the actual estimate is, and you don't want to commit to some decisions based on only uncertain information, then you want to keep your temperature relatively high. So there is this idea also of annealing this similarity of what you would do in annealing in a physical system. So once you pick an action, you execute it. And as a result of doing a thing, the system will return you a new context. So the kite will evolve, will give you a new observation. Notice that at any point, there is a need of knowledge of how this new context is produced. So it's just you are interrogating your system as an oracle, which is going to give you the next context. We're going to issue the reward. You don't need to know at any point what are the functional dependencies on what is the underlying dynamical system. Then you do a second step that you sample a new action. So this part is specific of this kind of algorithm. So we don't, but you repeat basically the same procedure without executing the action. You have a second, if you want a second sample of the action. And using these variables, you can compute quantities, which is called the temporal difference error. So what is it? Well, basically, it's the difference between the actual reward that you get minus this difference here is the estimated reward that you get. Okay, so the difference between what you will see in the future at time t minus what you see in the future from time t plus dt, according to your estimate q, is your estimated reward. So clearly this temporal difference error is going to be positive if you get a nice surprise, because your reward is larger than what you expected. And it's going to be negative if you get less than what you expected. So according to your result, you want to correct your parameterization. So the parameters that describe your Q function, which could be the parameters of a neural network, or could be just the parameters of a linear approximation if you select your own features. And then you're going to modify them in the direction of this gradient with a correction which depends on the temporal difference error. And then you repeat this for many, many episodes. And then under certain ideal conditions, you can prove that your system will converge to the optimal solution. If you're making strong approximations, so your function Q has a very low number of degrees of effective degrees of freedom, you will nonetheless approach some behavior which is as good as you can possibly get given the expressivity of your approximation. Okay, so how did we do this for our airborne wind energy production? So we are not going to use real data. Okay, we are going to use synthetic data. So we're going to create a virtual environment, a numerical virtual environment, which again, I want to stress. So we're going to generate data through a virtual environment. So this will be using equations like the Navier-Stokes equation to produce the winds, some dynamical system of what the kite does. But remember, the algorithm is totally oblivious to what is happening. Okay, so I could have tasked one of my students to generate the data, another one to build the algorithm, and they could not talk to each other except from exchanging data in a totally agnostic way about what the model is producing. So, but for practical purpose, we have to generate data to interact with. And we did this by making a poor man's approximation of the turbulent boundary layer by using a turbulent wet flow in which the top layer, which here we placed at a fictitious height of 100 meters, is traveling at a speed of about 30 meters per second. And then we are putting periodic boundary conditions in the longitudinal and transverse direction. The ground is clearly staying at zero speed. So this clearly falls very much short of describing properly what the turbulent boundary layer is, but it has the nice property that the winds increase, average wind increases with the height, and the system is inherently quite turbulent and unpredictable, which are the two key essential ingredients. Of course, if you use more elaborate models, if you use better models, results may change quantitatively, for sure, sometimes maybe even qualitatively. The point is that the method is not in itself limited, but by the goodness of the model that you approach. The performance might, of course. Okay, so this is our virtual atmosphere. And this is our virtual dynamics for the kite, which again is extremely simplified. The most relevant forces are hydrodynamic forces, which act on the kite, notably the lift and the drag, which have this expression, and in which there are these lift and drag coefficients, which you can just pull off some tables that give these coefficients for whatever kind of kite you like and you want to test. Then there is this tether, which connects the ship or the load with the kite. And here we assume that this tether is not sagging, that it's inextensible, and of course a lot more than this could be done. And then our ship is again modeled in a very, very naive way, in the sense that the only forces that are relevant are the weight and then the friction, a phenomenological friction exerted by the sea surface on the ship. I cannot stress enough the fact that there is a lot of interesting, fascinating, very difficult physics about the interactions of a structure with a wave and atmosphere that we are totally butchering here, because here we would just want to have a proof of concept that these algorithms are able to discover interesting things and could be in principle put to work in more realistic settings. So here on the right you see essentially graphically summarized the basic choice of features, the basic choice of observables that we want to adopt. And it's extremely simple. Actually, we're going to focus only on 3 quantities. All 3 of them are angles. The first 2 are quite intuitive. The first one is the attack angle. The attack angle is basically, if you look at the kite from the side here, the attack angle is the angle that it makes with respect to the vertical velocity. So the attack angle is very important in aerodynamics, because if you change the attack angle, you can make the kite or the plane or whatever, any airfoil, to dive or to rise. Okay, so that's one important variable, and the control of that variable can cause the kite to rise or to sink. Another important angle is the bank angle. So now if you look at the kite from the front, you can incline it sideways on one side or the other. So this operation is called banking on one side or the other. And when you bank an airfoil, the result is that when you increase the bank of an airfoil or reduce it, the result is that your structure will turn sideways. Okay? So changing the attack angle and changing the back angle induces a variation of the position of the kite with respect to the ship. And then, of course, there is another variable which we had an intuition that could be important, especially in a turbulent flow. That is the angle that the relative velocity makes with respect to the ground. Okay, which is basically an information about where this relative velocity is pointing at any time with respect to to a fixed reference system. And these are going to be the only 3 variables that we deal with. And of course, we are compressing all the knowledge about the system into very small effective state space. So when we started, we had no idea at all whether it could work or produce interesting results or not, of course, because that's a very crude approximation that we're doing here. Okay, so to summarize, the input for our algorithm is the reward. So at every time step, there is a distance that is traveled in that unit time. So a small step in a forward direction. And then we add a penalty if the kite falls. Of course, if the kite falls, then this is a failure. And we give a penalty, a numerical penalty for whenever this thing happens. So the idea is that the kite has to learn to do two things at the same time. First, it has to learn to stay up in the air in order to avoid this penalty. And at the same time, it has to gain as much traction as possible in order to let the ship progress in the direction of the mean wind. Of course, here it's very qualitative. When you go to quantitative aspects, it's very important how you frame as a function these quantities, but that's more of a technical point. So like I said earlier, we're just focusing on 3 contextual features: the attack angle, the bank angle, and the direction of the relative velocities. And the actions that we do are very simple. We just can change the attack angle or change the back angle. That's all that we got to do. And when we start repeating these episodes, you can see below, you see that at the beginning, the kite is either falling very early because it doesn't progress much, just a few hundred meters in the few minutes trials that we tried. So everything here in rescale times and lengths. But after a consistent number of episodes, you can see that sometimes it learns. Yeah, I see that there is a raised hand, please.
Yes, Antonio. I wanted to do something. So essentially, the kite does not anything about the fluid. The only information he has is its attack. Okay, implicitly it has information. So attack angle, a back angle depends on the fluid.
Yep, they all depend. They all depend on the relative velocity. Basically, all these three quantities here have inside the relative velocity.
Okay. Now I understand. Sorry. Okay, thank you.
It's a very local quantity, both in space and in time, and clearly you can think you can do much better than this if you include the other observables. But the point is that I hope I will convince you that even with such a restricted set of observables, you can see interesting stuff.
Okay, thank you.
Okay, so you see that sometimes it start learning interesting stuff. So 5,000 meters basically is the largest amount that it can travel, given the speed that it can reach, and the speed depends, of course, on the friction, on the weight of the load, etc. So it's by no means a meaningful quantity in abstract terms. But the interesting thing is that after a certain number of, sorry, I just want to click on this. After a certain time, then the performance stabilizes, and consistently, even though every episode presents itself with a different realization of the system, because the starting point within this turbulent wet flow changes from one episode to the other. We simulated this channel flow, this wet flow for several correlation times of the system. So notwithstanding the variability of the system, then you see that consistently this control is able to achieve a good performance. So what does happen in practice is the following. So this is a very crude visualization. You can see here, yeah. So this is the load, the yellow one. This is the kite. And you can see, I hope, that a typical behavior that sets in is to form some helical trajectory of the kite. Of course, these helices are very irregular, but that's a consequence of turbulence. So we did, I'm not showing them, but we did also learning in a synthetic flow which has no turbulence, just as a linear profile or a plug flow. And there we see clearly very periodic structures emerging. Here, the interesting thing is that sometimes there are helices, sometimes the algorithm decides not to do them, probably because it senses that the conditions are not interesting enough to perform that kind of behavior. So this is clearly adaptive behavior, and adaptive behavior on the, if you wish, on the local meteorology of what is happening in that particular time and place. Okay, so this goes on for a while, but I guess you understood what the message is. And you see that even though sometimes it gets quite close to the ground relatively, it's always able to catch up and keep going for this 5 minutes of simulation or whatever. But we cut it short. And then we go and look to some more quantitative features of this behavior, because in a sense we have found a way to control the algorithm. But the next step would be to understand what the system is actually doing, to find a simplified version of this control that allows us to really get a sense of what is happening in the system. So the first thing is that you just want to look at the dynamics of your relevant observables, which are the curves here. So you can clearly see that there is an initial stage here up to 3 or 5 seconds. This is a transient because we are initializing our kite in a position in space, which is chosen somehow. And we didn't try to optimize about the way to position the kite at the beginning. We just set some initial position. The kite is, the load is anchored to the ground. The kite is flying somewhere high. And then we release the load. And then the system has to learn how to make this transition And then you can clearly see that after a few seconds, it sets itself into this approximate cyclical behavior in which the attack angle here, the blue line, is basically unchanged. Whereas there is a clear anti-correlation between the relative angle, which is the green curve, and the bank angle. Okay, so this clearly points to some to the idea that there is some simple explanation of what is happening here. Okay, so this is a more pictorial, I don't know how successful it is, way of seeing this in the three-dimensional space of our observables. You see this part is the transient, this initial part, and then the system sets itself into this cyclical behavior, which okay, it's probably more difficult to understand than the graph above. So this motivated us in trying to find an explanation of what is happening. So the beauty of having such a small number of features is that you can extract now by hand a surrogate policy which approximates the policy that the algorithm has found, and it's much more explainable. Of course, if you had a system, I don't know, with 10, 12 degrees of freedom, you could have done this automatically by principal component analysis and some other dimensional reduction. But in this case, you can really do everything by hand. And how do you do it? So there's a lot of information here. So let me walk you through these different graphs. So the starting point is that you look at what are the bank angle and the beta angle occupancies. Okay, so the attack angle is constant, so we ignore it now. We remove this 30 degrees of degree of freedom from our system. We will keep the attack angle constant. So the idea is that on the kite there is some feedback controller that we do not describe that keeps the attack angle fixed. Okay, this is what actually happens in real planes. So you control the attack angle like that. So and we see clearly that there is a tendency to occupy. So these are states that are visited during the transient, but when the cycle steps in, there is a tendency to occupy these sets of states. And the fact that the curve has a negative slope is what expresses the anti-correlation between the bank angle and the relative wind velocity angle that I was showing in the previous slide. So based on that, we decided, okay, but let's just simplify our decision making in a very simple way. Let's keep the attack angle fixed, like I said, and then whenever the system has a certain bank angle, so when it's inclined on one side, and when the relative velocity is anywhere between -90 and 90, we are gonna make a decision, and this decision is gonna be, for instance, here, change the bank angle because the attack angle is fixed. So here you're gonna increase the bank angle in the yellow area. Here you're gonna decrease the bank angle in the purple area. And when there are these green squares with the white circles inside, you just stay where you are. So clearly, the idea is that this kind of procedure will probably reproduce a kind of occupancy like in this system here. And so now that we have a policy, which is doesn't come necessarily from a priori intuition, it's just a sort of distillation of in terms of rules of something that we have found empirically through the algorithm. Then you can compare the performance in terms of distance. First, here you see the learned policy. So here you can see the mean, the average, the median, and the quantiles. I guess it's this should be the 75 quantiles. I don't remember exactly, but yeah, this gives you also a sense of what is the excursion in performance, which is quite consistently good. Then you can go. Oh, sorry. So this is a trajectory obtained from the distilled policy, and you see that it resembles pretty much the one that qualitatively, the one that we have obtained with the learned policy. But we also see a drop in performance here. You see that this is significantly different, not by much. I mean, typically kites with this policy don't fall at all, but they lose something, some, I don't know, maybe 10% performance, slightly less maybe. So one thing that we realized is that this loss of performance was probably due to the fact that we are not properly describing the transient part. So this initial transition from the initial condition to the cyclical. So what we did is that we made a hybrid policy in which we follow the policy learned by reinforcement learning in the first 10 seconds, and then we switch to the approximated policy, to the distilled policy. And we see that we basically recover exactly the same performance. So in fact, this confirms that if we paid more attention, if you wish, also to a way to represent the initial transient, then we could have reached basically the same kind of performance by this very simple set of rules. Of course, why we didn't do this? Because the transient depends very much on the way you initialize the data. So unless there is a very good argument to say you should initialize your kite in that position because that's what we do with chips for real, then the exercise, otherwise the exercise is a little bit moot. But you can clearly understand that the same kind of techniques could be used. Okay, so time to wrap up. I hope I convinced you that reinforcement learning has a potential to discover useful, effective, and explainable control strategies for a problem of, I think, primary technological importance, which is airborne wind energy production. What we are currently doing now, we are tackling the problem of the power station, the ground power station. Like I told you, this is a situation in which there are two sequences of decisions that have to be made. So you have to understand how to maneuver the kite when the tether is being unrolled, which is the energy production phase. You have to learn when to switch from the energy production phase to the recovery phase, in which you pull in the glider here, when to do it and how to do it. So are you going to pull it just keeping a fixed posture, or there are things that you can do in order to reduce now the energy consumption when you pull it in? How do you switch from one behavior to the other, and how do you put all these items together in a full control for this energy production system? So this is ongoing work, which I hope I will be able to tell you in the next occasion. So we are also investigating, like I told you before, what is the potential of using more general, I mean, really more truly model-free approaches in which there is not even expert advice injected in the system. And like I told you, using deep Q-learning is one possibility. Deep Q-learning typically finds reactive strategies. So these strategies are local in time. So they are based on features that are discovered by your neural network, but these features are instantaneous. So decisions are made by using instantaneous information about your system. But of course, you can imagine that since the system has many timescales, you know this very well, it would be useful to discover strategies that somehow depend, have a temporal memory of what has happened in the past. And if you want to do this, you have to use other kinds of neural networks, recurrent neural networks, or of the kind that have been used, for instance, in language processing, long short-term memory in recurrent networks, or maybe transformers, who knows. A big question mark when you do all this is that assuming that we have enough data to train our system, which is a challenge in itself, and enough computational power, how do we explain the performance? So if it's really performing better, what is actually measuring? So how can we extract this information, then boil it down to a real understanding? Because predicting is good, controlling and predicting is fantastic, but it's not understanding. And therefore, at some point, one has to open the box. Okay, that said, I'm ready to give the floor to the audience if they have any questions, and I will leave you with this nice short clip that shows that kite surfing is not only interesting, but also fun, in case you have this experience already, you will know what I'm talking about. Okay, thank you very much.
All right. Thanks a lot for this wonderful talk. So we can take questions if there are any in the chat, or you can raise your hand and ask your question. Yes, Guido.
Okay, can you hear me?
Yeah, sure.
Oh, ciao Antonio, so nice to see you.
Yeah.
So a very simple question. Have you tried to use this the procedure that the policy that you learn with a given wind? What happens if you change the wind by a factor of 2, for example? Do you need to learn again, or is able to generalize?
Thank you, thank you. This is an excellent question. So this is a question that technically goes under the name of transfer learning. So if you learn in one context, how your solution is applicable to different contexts. So I don't have a full answer for that. I can only tell you that we tried with rescaling the wind speed in 2 directions, and the qualitative features remain the same. Of course, if your wind speed goes is too little with respect to the length of the kite, so then you do not have thrust enough, you do not have lift enough, and this really doesn't manage to learn properly. So I think that the proper statement is to say that conditional on a reasonable variation of parameters, it's quite stable. But of course, you would, if you want to consider really for highly variable conditions, which is a good idea. One approach that you can take is that you can basically construct different policies for different situations. Okay, so that if you train for different settings, and you have some sort of information which is able to give you a hint about in which of these domains you are, then you can sort of decide for instance, by sampling the average wind or the relative velocity, the magnitude, you could decide I'm in a situation of low wind, I'm in a situation of strong wind, and I could move on from one. So this is something that we did in more detail in the previous work with gliders, and we could see how policy change depending if the turbulence is strong or weak, and this could provide a handle to switch from one set of policies to the other. But that's definitely a very good question.
Thank you. Very nice.
Massimo, you can unmute and ask.
Yeah, I was curious to when you did the comparison between the distilled policy and the reinforced learning policy. So you convinced us that the main difference is due to the transient. But just to understand, because what you do is that when you do distilled policy, you place the kite at the given height with a given bank angle, and then you decide that is the bank angle, that the attack angle that I keep constant, and then I adjust the others. While so so the difference here when you use when you switch the policy is that the kite has to find the proper angle of attack for the condition, and then which may be different from the one which was originally, and then you can exploit the policy.
That's correct. That's correct. For this particular choice of initial condition, you can see here, the attack angle actually has to learn to go from here to here, and then it stays constant. So this is something that our distilled policy doesn't do, because it starts at 20 at the beginning.
So in each episode, the attack angle would be different according to the condition where, okay.
Yeah,
okay.
And also the length of the transient may vary a lot. So sometimes there is a longer transient, which takes tens of seconds before setting into a cycle. So there's a high variability on the extension and the quality of this transient. But again, it's mostly a matter of how much energy and time you want to spend in this, because you could partition your decision-making process into two stages. One is finding the approach to the stationary dynamically cyclical solution, and then keeping it.
Okay, thanks a lot.
Greg, you can ask your question. Yeah.
Yes.
Yeah.
Hello, thanks for this beautiful talk. Makes many of us wish we could go out kite surfing. I wanted to ask, this seems like a great context in some ways to push the machine learning to one of its challenging points, which is that if you're in this system, it's precisely the rare events where you're most concerned about, that your kite doesn't either hit the ground or break your cable or something like this. And I've wondered if you've thought a little bit about how the learning process can be trained to be sure to handle the rare events correctly, even if it maybe doesn't optimize the simpler metrics.
Okay, so yeah, so okay, there are many layers to this question. So one first very general idea is that we are always here optimizing average performance. Okay, so basically we are okay if the distribution of performance is wide enough, as long as the average is good. So it turns out that the distribution is not so bad eventually. So you see that there are fluctuations of the order of 10% here. So but there are excursions here, there are points, and there are times in learning, especially in early learning, where failures occur. Okay, so you could also cast the problem in a different way, in a more risk-sensitive way, and you could ask for what are the policies which are most risk-averse. I don't risk dramatic failures, because if my kite falls, well, fine. If I'm using a glider, well, that's a plane falling, and you don't want to do that. So one thing that you might be interested in is changing the setting in such a way to address risk-sensitive objectives, which you can do by several classical techniques. Second thing is that remember that these kites are extended objects, so they are several tens of meters apart. So they also do a lot of filtering, and very dramatic fluctuations are smoothened out by the object itself. Moreover, you don't expect to be flying kites if there are really obnoxious winds around. This is something that you don't want to do anyway.
May I ask?
Yes, please go ahead, Andrea.
Oh, ciao Antonio, pleased to meet you.
Ciao, Andrea.
Ciao. Very interesting. Thank you very much, first of all. When you spoke about wind turbine, you mentioned that they are static. Actually, they are, in a sense, dynamical. The dynamics can be rotate around the axis, and then they can also be slide down. Imagine to have a very strong wind, and this is dangerous. They can reduce the velocity. So the question is, can you apply your strategy in a way to optimize the rotation and the slide down of the turbine in a park, just using your strategy?
Yes, you can. I think that this also has been done in some attempt in a computational setting. Again, if you have a model of your turbine, you can, because the big difficulty of doing this in real systems is that you have to do something different. Okay, still within reinforcement learning, but you have to do something different, because you can easily imagine that when I showed you here this graph about the performance, okay, this is several hundred thousands of episodes. Okay, each of which in real time would be minutes. And so if you just take this straightforward approach, in a real setting, this would take forever to train. So you have to do something different. You have to use many kites together in order to speed up learning. You have to do other techniques in which you do some sampling online and then turn to computations offline. You have to do mixed strategies. But apart from that, there is no intrinsic limitation of using reinforcement learning for any kind of energy device. The point I wanted to make is that not really that there is absolutely no adaptivity in wind turbines, because I know there is to some extent. The point is that, for instance, you cannot deploy. Sorry, just a second. So you cannot deploy them wherever you are. So, for instance, one thing that we are very much concerned at ICTP is that this kind of energy producing device could be deployed in developing countries because they are not expensive. They can be moved from one place to another. It doesn't give you a lot of wattage. So remember, the scale of the amount of energy that you produce is not comparable to a wind farm or a turbine. It's something much smaller, but much more agile. So I think that the merit stays in that. And anyway, I think that the kind of controls that you're using for kites are but this is more a personal, more adaptive than the ones that you can have on a big turbine. So you can, it's a system which is very agile. If you pull one of the lines, it reacts in times of seconds. Whereas, of course, there is a substantial inertia in wind turbines that again averages out in time the kind of response. So if you wish, I could describe the kind of control that you do for a wind turbine is more of sort of climatic. So it senses the weather on a longer time scale with respect to the meteorological control that you have with a kite, micro-meteorological control. I know I'm using these things improperly, so I know you're an expert, so bash me if this is not what I meant.
Thank you, Antonio.
Filippo, you can go ahead.
Yeah. So, ciao, Antonio. So the question is, okay, of course, the nice thing in this kind of approach is that you don't really care about the features in the flow, but I wonder if you have tried to see what features are important for the, what features if there are features in the flow that the kite follows, if there is something you try to do, maybe filtering the turbulence and see what scales are important, this kind of thing.
Yeah, no, we did not do that. So like I said earlier, we've been using just very local in time and in space observable. One thing we did is that in some attempts we added acceleration, and there was some improvement, but this improvement comes at the expense that if you add the additional variables, then training takes longer. And therefore, there is a trade-off between selecting a large number of observables, but then having longer computations, longer training, a substantially larger amount of time in trying to tune the hyperparameters of the algorithm, such as learning rate, temperatures. So in the trade-off between enriching the observables and simplifying the setting for quick learning, we sort of leaned on the side of having a more compact system. I'm 100% sure that there are a lot of things much smarter than that, relying on observables which use the coherence of the structures that are available, the time correlations. How to do this in a way that is not totally black box, it's still not entirely clear to me, but definitely a challenge.
Okay, grazie. Thanks.
All right. So then I'd like to, I don't think there are any more questions, and we are also over time. So I'd like to thank again Professor Celani for this talk, and also Professor Volpe and Professor Bifrale for their talks in this session. So thank you all for your presence, and thanks for these wonderful talks.